research question we try to answer in this work is how can we use meta-learning to learn a good exploration strategy in a contextual bandit setting. So let me start by setting up the stage with the definition for contextual bandits. Contextual bandits is an interactive learning setting where you have an interaction between a learning agent and an environment. And here I will show how this interaction may happen in a simplified news article recommendation system. So the system has access to a set of news articles, as well as context feature vectors representing users. And the task at hand is to choose one of these news articles to recommend for the user. Having recommended an article, the system gets to see some sort of reward signal. For instance, how much time the user spent reading this article, or whether the user has clicked on selected article or not. Our main goal is to maximize the total sum of observed rewards in this interactive setting over different rounds. And a fundamental problem in this setting is learning when to do exploration. The way we go about solving this problem is using a meta-learning technique where we, at meta-training time, we assume access to an expert to exploration strategy that effectively cheats by knowing when to explore and when to exploit. We construct this expert policy here in this figure. It's called PyStar by simulating contextual bandit tasks on fully supervised synthetic data sets. So what we do is at every training time, at every time step T, we query this expert to know whether we should explore or exploit, and then observe the long-term return, and use an imitation learning algorithm on top of all of this to imitate the behavior of this expert strategy. So a fundamental question is how can we generalize at meta test time when we don't have access to this expert? And the answer to this question is that we use a different set of features that are task independent, but generalized across a different set of contextual bandit tasks. So these features include some measures of uncertainty and confidence that the learned policy use to estimate its confidence about the predicted action. We also keep track of different statistics for observed loss for different selected actions so far. We compare our approach to alternative exploration strategies in contextual bandits like Epsilon Greedy, LinUCB, Tau First, and Cover. And we conduct experiments on 300 contextual bandit datasets. These are simulated from multi-class classification problems. And we outperform alternative strategies in most settings. Just to give you a glimpse of the results, here in the first row, our approach outperforms Epsilon Greedy on 30 or more datasets in win and loss statistics. We also provide theoretical guarantees for our work, showing that the imitation learning, the no-regret imitation learning guarantees can also be leveraged in our meta-learning setting. So in conclusion, we present a meta-learning approach for learning how to explore in contextual bandits. We solve this problem using imitation learning. And we generalize using a robust set of features. We outperform alternative strategies in most settings and provide theoretical guarantees for our work. And with that, I would like to conclude. And our poster is here to your left, to your right. And thank you so much.